5 and 6?
For the first couple of problems, I think I fixed those, but I'm not real sure what we're supposed to do with 5 and 6.
Okay. Well, let's go back, because there's actually a couple, still a couple open questions from other students on questions 5 and 6 for problem set 2. So let's go in here. Office, courses. And, since we're this far along the course, I am going to go ahead and just show the actual solutions. Al Frazier supplied me with those, and I don't think there's really, at this point, a whole lot of risk in cheating, for lack of a better word. But he's obviously put a lot of work into this. Okay, so this is going to be problem 5. Does that look familiar? Good. Margin of font. Mechanical device will cost $20,000 when purchased.
Yeah. It's just a whole lot more up there than what.
Yeah, it's okay though. He's put a lot of, this is a really nice looking solution. So let's just take a look at it. Maintenance will cost $1,000 per year. The device will generate revenues of $5,000 each year. At the end of 5 years, the salvage value is expected to be $7,000. What is the net present value of this proposal using an 8.3% discount rate? Okay. So first of all, let's just start from the top and make sure every number on the spreadsheet makes sense. So here's your 8.3. You're going to run for 5 years. So here's your $20,000. It's going to cost, and that's pretty easy. The present value is $20,000. And what he's done, he's just multiplied it by -1. And if I go into the formatting, well, he used custom, which, oh, I see. I like his custom. So this is an engineering format. And it's also got the parens built in, so if it's negative, it goes into parens, which is kind of standard accounting. So that's why it looks like that.
Well, I just put -20,000 in it.
That's fine. Yeah, that's fine. That's fine. But what he's done, he sort of said, I'm going to put this in. And so he's done it in such a way that his inputs are pretty tidy, and he's got good explanations for his outputs. Right. Okay, operation and maintenance cost per year. Now, what's the present value of that? Well, let's just take a look. So he's pulling that from down here. The annuity is $1,000. So he's just taking that $1,000 and taking it times -1 because it's negative. The factor, so he's actually used the full equation from going from an annuity to the present value. And this always seems a little strange to me, but because I would think, oh shoot, I'm going to need more than $5,000 now because the money's going to become worth less. Right. But I think the idea is if you've got the 5,000 and you're actually able to invest it at 8.3, good luck with that. You're making money, so you only need $39.61 right now in order to pay $1,000 per year because you've got it invested at 8.3. So this is a PA calculation. And it's negative because it's operations and maintenance. Is that?
I'm not sure how he's getting 3961.
From 1,000? Let me go back to mine. I'll just double check with mine. I'm just going to double check with mine. Learning unit 1. Now let's go to equip. Okay, I've got it right here. So what did we say? 8.3. Five years, 1,000. Okay, so that's what I get to. Oh wait, yeah. 8.3. Yeah. So in the top, I've got the full expression. At the bottom, I've got, I guess, the full expression too. And we can do it, let's do it one other way here. Let me try this. Net present value. I want to see what the related functions are. Let's see, let's do financial functions. Oops. Financial functions. So I'm going to try PV based on that. PV, so equals PV. The rate is 8.3. The number of periods is 5. The payment is 1,000. Boom.
My formula must just be wrong.
Okay. You know, so I think at this point in the course, though, we can go to the PV function. Use PV. Yeah, I would just say use PV. Yeah.
Because right now I'm looking at it and it's, it's this thing.
No, I know, it's a big giant mess. Yeah, I know. I was too, yeah, it was, so this giant mess equals that.
Right.
It's the PV with the 3 arguments. Okay, so the function's working. So just, go and use PV instead of the thing. Okay, so the 3961 is it's It's not an asset, it's a liability, so it, like the 20,000, is negative. The revenue, so we're going to make 5,000 per year. Let's look at that. So you might say, okay, so neat, 5,000 per year. Times 5 years, that should be what, $25,000, but it's not 19. And that's because, I think that's because that's money you haven't. It's money you haven't made yet. But if you were to have that 19.8, you could make 5,000 per year at 8.3%. So you have to treat each one of these the same way.
Right.
It's actually less than you would have thought. Okay, and then the salvage value. I don't know if there's a PF function or not. Future value. Let's see if we can find present.
NPV.
Well, a series of periodic. We're actually looking for just a single payment. You might be able to do. Let's see, what's PV? Future value, let's see what, optional. Future value or cash balance you want to attain after the last payment is made. 0. Yeah, I don't know what that one is, but might be able to. Maybe let's try it this way. I bet we can try it this way. I'm needing a challenge right now. Let's try this. NPV. Let's try this. I'll mess up my own sheet. Equals NPV. The rate is 8.3. Value 1 is 0, 0, 0, 0, 7,000. 10 cents. Let's try this. 0.83. 341. 83. 083. 1,000. Nailed it, I think. 46.98. There we go. So I did that?
No.
Let me show you. Yeah. So I used the net present value function, and the net present value function requires that we type in the rate. So the rate is 8.3%.
Type it in, or can you just?
Well, you could also click it over here. Right. I mean, I could have clicked it there. Yep, I get the same number. The first year it's worth nothing because I didn't sell it.
Okay.
The next year it's worth nothing because I didn't sell it. Nothing, nothing. So it's worth nothing for the first 4 years.
Oh, so.
And in the 5th year I sell it.
It's $7,000.
7 grand, and here comes my answer. Net present value.
5,088.
For 7,000, let me just see.
1, 2, 3, and then 0.
Got it? Nice. Okay, so that's how to use the net present value function. And let's go back to Fraser's solution. Five years, so right now the project is worth $544. Yeah. So that should sort of tell your initial investors, like, hey, you know what? We need $1,000 to break even. If you let it, and it seems like with this guy, if you let it run for longer, if you're only spending $1,000 in maintenance and you're making $5 grand a year, it should make more money.
Right.
Ready to move on?
Sure.
Problem 6. Okay. Problem 6. Assume that the PV system in problem 3 generates 1,100 kilowatt hours of AC per year for each kilowatt hour of DC. So I saw a couple other students had trouble interpreting this problem, and this is why I'd love to go back to the picture. So let's just say you've got 1 watt of DC coming into the system. Now let's just say 1 kilowatt. 1 kilowatt DC. What that says, right. For 1 kilowatt DC, and that's actually power. That's the power rating of the panel. Okay, so this is where it gets a little confused, because that the power rating is 1 kilowatt hour, 1 kilowatt DC. That's going to give you 1,100 kilowatt hours of AC per year. So you're actually going from power to energy. Yeah, and so if I had 6, it's going to go to
600.
Exactly. So it's it's a little confusing going from a power to an energy, but really what's happening is you're in fact integrating over time. And I know we've covered this before, but just to look at it, energy equals the integral of power as a function of time. From 0 years to 1 year. So that's exactly what we're doing when we integrate or add. Add.
Yeah, that wording kind of messed me up.
Yep. Yep. It's what separates the. Anyway. This is average. So, there he goes. So the system size is 6 kilowatts DC. The salvage value is $7,000 in 15 years. I think that's given in the problem, right? The discount rate is 9%. The system lives for 15 years. It's going to generate 1,100 kilowatt hours per year. And I think what we should probably write in here per year, per kilowatt DC. It's a little more complicated than that, right? The utility is going to pay 15 cents per kilowatt hour. Let's see what that format is. Accounting. I guess the accounting puts the dollar sign way over there. Okay, fine, so fancy. Okay, so the total yearly generation, we're looking at the size of the array, which is 6 kilowatts DC, times the factor to go from, so 1,100 kilowatt hours per year per kilowatt DC. Yeah. All right, the annual utility payment. If you're making 6,600 kilowatt hours and they're paying you 15 cents, you get $990 per year.
Yeah.
The annuity salvage value, okay, so PMT is the equivalent of A/P. So there are 3 inputs. B7, which is the discount rate, goes in first. B8, which is the lifetime, goes in second. There's nothing in the third slot, and the next one is the salvage value. So let's just look up PMT equals negative PMT, open paren. Here goes the rate, 9%, number of periods, 15. The present value, we're just going to leave that blank because we don't have the present value. The future value is $7,000. There it is. So you could have $7,000 in 15 years, or you could have $238 per year. Okay, so the total annuity value is just the sum of those two. It's whatever, it's essentially what you're going to make in the future off the salvage plus whatever the utility's paying you.
That's can you say that again?
So the total annuity value,
Which would be the
whatever the
present value.
well, no. Yeah, what we did, we figured out how much energy we make per year. Let me see if I can make that a little larger. We figured out how much energy we're going to make per year. We know that we're going to get paid 15 cents per kilowatt hour for it. So we're going to get $990 per year. We also know that at the end of 15 years, we're going to be able to sell the system for $7,000, which is the same as making $238 per year. So what I did over here, I just showed off to the side this function. It's PMT, and that's the rate, that's the number of periods. There's no present value, but here's the future value.
Got that.
Dang, okay.
So the total annuity value is that.
The annuity value is $12.28. And so the next present, the net present value, so we have to turn that annuity into whatever it's worth now. Yeah, so the rate is again just B7, that's the 9%. The payments, number of periods is B8, that's 15. And then the payments are given, it's that $12.88. So that's the net present value. Getting it?
Do that one more time?
Sure. So to get the yearly utility payment is the 15 cents per kilowatt hour times the 6,600 kilowatt hours per year. It gives us $990 per year. The salvage value in 15 years is going to be $7,000, which is the same as $238, and we use the payment function. And so I just demonstrated it off over here too. The payment function is the rate, which is 9%. Number of periods is 15 years. There is no present value, so there's just a blank there. And then the future value is $7,000.
So then the net present value is all of those added?
The net present value takes the annuity, which is here, and turns it into the present value. So that's also a function. And the function is the PV, the present value function. So you give it the rate of 9%, you give it the number of periods of 15, and then you give it that payment, which is the sum of the two annuities. Did you get 99 out too?
We got 9,898.53.
Let me just look here.
Salvage value.
You got your 990 there. Where's your 238?
Annual salvage value.
Oh, yep, okay, 238. Then where's your sum? 22, 28, okay, perfect. And then where are you aiming for your answer right here?
Yeah.
This is the, double click it. Rate, years, okay, 15. Looks like just a rounding error.
This is probably, yeah.
Yeah. The accountants argue over that one.
Not an accountant.
Yeah. All right, is that good?
Yeah.
Okay, super. Let's put a fork in that one. 30 minutes, perfect.